Hello and welcome back. Today's video is a continuation of previous video episode 19. It is a second part of project of building infrared detection circuit. First part was dedicated to theoretical explanation of why and how components function in the circuit. Today's video will be practical implementation of all the knowledge and information we learned and gathered in the first part. By using breadboard and some common components we will assemble functional infrared detection circuit. We will also take all sorts of measurements of voltage and current, to experimentally verify our math from first video. We will also use S01E20 oscilloscope to observe output signal. So, let's get on to the video. If you enjoy practical electronics tutorials like this one, please subscribe to the channel. Don't forget to like the video and enable notifications so you don't miss future projects. Thank you. If you have not seen previous video, episode 19, we strongly encourage you to view it first, and then come back. Episode 19 contains all of the theoretical background, math, and explanations of how and why we used components in the design of the circuit. In this video we will prototype our circuit using breadboard, 3 resistors, indicator LED, infrared LED, phototransistor, NPN2N3904 transistor, connecting wires, and power source. This is the layout of assembled circuit on the breadboard, so let's analyze it. We connected 2 breadboards together just to make extra space. If you have only one breadboard, that is just as fine. You can implement entire circuit, just pull components closer together, and adjust layout to match your needs. We have provided 5 volts DC power source to top and bottom rails of our breadboard. Red and black lines indicate positive 5 volts rail, and ground rail, respectively. In order to filter out any noise that power source can introduce into the circuit, we have short-circuited positive and ground rail with 0.1 microfarad ceramic capacitor, marked 104. Please, make sure you use ceramic, non-polarized type of capacitor. This capacitor is not in any way absolutely necessary, but it helps get a cleaner signal on the oscilloscope, especially if you are using any type of AC to DC converting power source. From previous video, you will recognize that this is implementation of our infrared light beam source. This part of the circuit is implemented by using infrared LED diode QED234 and 150 ohms current limiting resistor. Together, they make source of our infrared beam. The function of the resistor is to limit current going into infrared LED to 25 milliamperes. We have provided schematics that this part of the circuit represents. The choice of components and their values are based on recommended best practices and electrical characteristics obtained from components datasheet. Next, we have our infrared receiver. This part of the circuit is implemented by using QSD123 phototransistor, with 10 kiloohms resistor in series. Together, they form receiver part of the circuit. We have provided schematics that this part of the circuit represents. Choice of 10 kiloohms resistor is based on current generation, necessary to properly bias NPN transistor in detection part of the circuit. And at last, this is our detection part of the circuit. The function of this part is to switch on or off the indicator LED, based on occurrence of triggering event. We have provided schematics that this part of the circuit represents. While infrared beam remains uninterrupted, the LED is on, signal remains low, and it remains that way, until triggering event occurs. When triggering event occurs, the infrared beam is interrupted, and detection part of the circuit generates high signal to indicate triggering event. Also, the indicator LED switches off, for the duration of triggering event. This part of the circuit is implemented by using NPN2N3904 transistor, white LED indicator, and 150 ohms collector current limiting resistor. For your convenience we have provided an alternative view of our implementation of the circuit. Please take all the time you need, pause the video, and analyze connection and layout of the components. When you decide to implement and test this circuit, please have in mind that infrared diode and phototransistor have to be in perfect alignment, otherwise, you will not get a full base current, necessary to drive NPN transistor in saturation mode of work. If your implementation differs in measured values, the alignment between these two components is main and only culprit. The rest of the circuit is pretty much error-free. Also, absence or presence of daylight has no effect on behavior of the circuit. Both, infrared diode, and infrared receiver are insulated from effects of daylight, or any source of artificial light, in general. Now, let's hook up our S01E20 oscilloscope, and power on the circuit. We will connect oscilloscope probes to collector and ground terminal, respectively, as we have shown and explained in previous video. We will simulate triggering event by inserting metallic obstacle between infrared diode and infrared receiver. Each time that triggering event occurs, our indicator LED will go off, and signal on the oscilloscope will go from low to high, for the duration of the event. We recommend you set time delay setting on the oscilloscope to 0.2 seconds. Duration of high signal is equal to duration of triggering event. Now, to verify our results, let's take measurement between collector and emitter junction of our NPN2N3904 transistor. If our math is correct and circuit design is sound, when infrared beam remains uninterrupted, our NPN transistor should be in saturation mode, and collector-emitter junction voltage should be between 0.2 and 0.4 volts, per datasheet. This voltage should represent our low signal. When infrared beam is interrupted, collector-emitter junction voltage should jump to around 3 volts, which represents our high signal. Our multimeter verifies our result, so our design is sound, and math is correct. Now, this was a lot of fun. We have successfully designed and implemented our infrared detection circuit. We have observed on the oscilloscope a signal generated by the triggering event, and we have verified our math with readouts from NPN collector-emitter junction with multimeter. In next video we will remove source of infrared light, the QED234 diode, and leave only receiver and detection part of the circuit. We will use this new design to test function of TV remote, so stay tuned. Please, before you leave, show your appreciation by liking this video, leaving a comment, sharing it, and please subscribe to the channel. Thank you, and see you next time. Bye.